Hello, everyone. I'm Larry Lai from Penang Technology US Research Lab. Today, I'm going to talk about artificial intelligence with remote sensing by applying deep learning to image enhancement, analytics, and it's a business. Here's a quick introduction of myself. I'm a staff research scientist in Penang Technology in Silicon Valley. I lead a team working on AI plus remote sensing, especially focus on image enhancement, model generation for object recognition, segmentation, and multi-modality modeling for applications like crop yield forecasting and natural disaster analysis. For my personal research publication, I have published over 27 papers on computer vision topics and also over 33 US patents. I have a personal webpage, www.larry-lai. In this webpage, collect some interesting research demos. So you are welcome to visit and have some feedback. Okay, so about Ping An Group, many people may never heard about Ping An, but Ping An is the largest insurance company in the world. So in 2020, it ranking 21st in the Fortune Global 500 company ranking. So if you've ever been to Shenzhen, so the highest building in Shenzhen is Ping An Finance Center. So about the primary business of Ping An, including insurance, banking, financial services, and healthcare. Now, Ping An try to empower each sector with technology. Here's some example of remote sensing application in Ping An Group. So the first is agricultural insurance department. So they need remote sensing to detect the ground crop type and the ground cropland size. And next is smart city department. They need remote sensing to detect the green field in the city and even the building construction progress. And about investment apartment, they need remote sensing for the crop option trading because they try to predict the future crop yield in the next few months, and they can trading in the market. Last is ESG department. ESG stands for environment, society, and government. So they care about the air pollution, ground usage. For example, we conduct carbon dioxide analysis for each county in China in the past years. Yeah, so there are a lot in application in Ping An. So we call it a closed loop. So it means as a research lab in Ping An, we have many innovation or new ideas. So we can easily deploy our idea to the business application, and business application can give us a real feedback. For example, they can feedback how's the accuracy of our model output. And with those accuracy evaluation, we can easily upgrade our model. And even sometimes we can come up with a new idea which never been surveyed before. So I think we are quite lucky as a research lab in kind of company, but with a lot of application. Okay, so here's the outline of today's talk. First, I'll talk about the PAI super resolution model, which can enhance 4 times image details. Next, I will talk about the haze removal model. So we talk about how do we design a model to remove the haze occlusion in remote sensing image. Next, I'll talk about crop recognition model. And last, I'll show some analytics, which are interesting in Ping An Group. Okay, so the first challenge in remote sensing is we talk about is image resolution. As we show here, if we talk about 10-meter resolution, which means each pixel size on the image means 10 meter in ground distance. So which means each pixel is 10 meter long on the ground. Some application like road or car detection need high resolution images. So there are 2 kinds of image source. One is public, and which means free, like Landsat satellite from NASA and Sentinel satellite from ESA. So the free images resolution from 10 meter and above. So we call it is a low resolution image. Yeah. So this low resolution image can use for green field detection, forest analysis, but sometimes like road segmentation or crop recognition, we may need higher image resolution. So in this case, we may come to commercial companies like Planet Lab to have the 1 meter resolution images. But here's a problem. So data cost is very high in purchasing those high resolution image. So this example on the right is a 10 meter free, low resolution images. But for example, if you want to purchase a high resolution, like 1 meter resolution, the data cost is very high. It may from $8 per kilometer to $15 per kilometer. So when we doing the like great massive area like the Grand China or maybe a US cropland detection, those data costs will make us become a mission impossible. So here's our first challenge. We are thinking if we can train a model, design a model, which super resolution model. With this model, we can enhance image detail. For example, this model can input a low resolution, like 10 meter resolution, and the model can output 1 meter resolution image. So this is our ideal model, shows here, and which can we can think about how does the model can reconstruct this missing information, right? So this is a very interesting question. This is quite blurred, and how the model can reconstruct such detail in the image. So here's our idea. The first for the input for the super resolution model is we need to collect many low resolution images and high resolution images. Our idea is try to make the model learn the pattern correlation between low resolution and high resolution. So in this example, we may collect thousands, hundreds different images, and the model try to learn how the correlation between these two different images. Next, we also collect some image changes in temporal domain. So this example, because we find the same geolocation, but with different capturing time, like the image shows here, the model can learn the detail from different lighting changes and even different ground changes and occlusion. So in this example, the model maybe learned those, this is an airport. The airport detail need to enhance, but instead of the water or even the occlusion area. So this is our idea. We try to collect many image with different timestamp, and those image may contain different lighting conditions, which can make the model learn some detail. And third is we try to leverage the other sensors, like the SAR. SARs means synthetic actuator. So the SAR provide much different images on the ground. For example, this is RGB images, and this is SAR. So the SAR image can have much detail about the like building, road. Yeah. So especially with this, we call it attention from some we are interested target, and we can use this attention to enhance the RGB image. Yeah. So this is our third idea. Try to leverage the other sensor. Okay, so we come to our proposed part. Here we propose the Pi super resolution data set. In this data set composed of Sentinel-2 multispectrum images, which include 4 different bands, BGRN, and they are 10 meter resolution. And we also include 4 different temporal capture, 4 different date. And it also includes various terrain coverage, like some is a cropland, some is a city, some is a forest. So next, in addition to Sentinel-2, we also, the data come with the Sentinel-1 SAR imagery. The SAR image include 2 bands, VV and VH. Both are 10 meter resolution. They are geolocation aligned with Sentinel-2. And especially, we will try to design the left part as an input for the model training. And on the right part is target of the model output. So the target is a more high resolution image captured by the UAV, unmanned aerial vehicle. So the high resolution is a 4-band channel. And in the high resolution data, we have 2 different resolution. One is 0.6 meter and 2.4 resolution. So these 3 data sets, they are all geolocation aligned. So we can train the model and enhance. So the model can learn low resolution and high resolution. So here's some quick result of our trained model, and we call it Pi super resolution model, and it can achieve 4 times enhancement. And here's a result shows here. On the left is a ground truth of UAV, it's a 0.6 meter resolution. And in the middle is a bilinear interpolation 4 times from 2.4 to 0.6. And on the right is our model output. So compared to interpolation method, you can see our proposed model can have more detail compared to the interpolation model. And also compared to the ground truth is quite vivid and almost very visual, cannot distinguish the difference. And here also show the PSNR, because in our model, we leverage the GAN training, so the GAN can generate some more details, but GAN maybe have a problem. It can be different from the output can be much different from the original one. So we use PSNR as an index to evaluate how it's similar to our original image. You can see the bilinear method PSNR is 34 dB, and our model output also have very high 34 dB, which means the color tone of our model is very, close to the original one. But at the same time, we still can have sharp detail. So this is our model output. And in addition to test on the training and testing set, we try to do the model generalization. So the model I just showed in previous page is trained on Sentinel-2 10 meter to UAV NEP 2.5. But now we test our model generation on 40 meter to 10 meter. So this is the result showed. And in the middle is a bilinear interpolation, and on the right is our model output. You can see our model can still outperform interpolation method and even to the different resolution task. So in this case, which shows our model can generalize to different resolution. And here we do more model generalization to different satellite. Here is a testing our model on Gaofen to satellite. So this is an example Gaofen satellite in 1 meter resolution. And on the right is our model result. You can see that the comparing to the interpolation method, our method can preserve much more detailed. So it seems quite working well. So the model can generalize to different satellite. I think our model can generalize to different resolution and different satellite, which because we collect very big super resolution training data set, because we cover different crop length and even the crop type. So that's why the model learn a lot of general properties. Okay, so here's a quick summary of the first part in the super resolution imagery enhancement. So imagery enhancement, which can save a lot, especially for some application need high resolution images. So yeah, so I think this is a critical part for our application can really apply to the business application. Next, here we talk about, we propose a Pi super resolution data set. This data set, as we know, is the largest remote sensing data set, and which include over 1.6 image pairs, 1.6 million image pairs. And in the data set include 2 different 4 times scale images. One is 10 meter to 2.5 meter. The other is 2.4 to 0.6 meter. And we plan to release this data set to public in Q4 this year. So in Q4, I think we will release the public to public. If you are interested, you can reach to me. Next, in this part, we use the data set to train our super resolution model, which the model can achieve the average PSNR 34 dB. And from the evaluation, we can see the model effectively enhance the image detail and also can preserve the constant color tone compared to the original image. So we also test the model generalization to different resolution and satellite, and the results seems quite promising. So yeah. Okay, so this is quickly first part. And next I go to our pi haze removal model. So in in remote sensing, cloud and haze occlusion are very common. So this is a cloud occlusion showing here, the white pixels, they are all cloud. So the problem cloud causes is we cannot see the ground activity because those pixels just be, occlusion by the cloud. And the other, trouble is haze. The haze occlusion, it actually is more common than cloud. So this is an example with the haze. The image can look like kind of blurry and even the whitening, brightening. But the problem is with the haze cover, we cannot see the the true ground reflectance. Especially for crop growth monitoring, we use NDVI index as the growth index. So the haze problem can make NDVI index incorrect. So this is a serious problem in real application. And we also know that cloud detection and haze removal is not new to the research. And especially for like Sentinel-2 level 2A product. ESA claim this product is already haze-free, aerosol-free, and cirrus-free. And from our true observation, we find in L2A product, the cloud mask or cirrus mask is accurate enough. So we can, for example, list all the cirrus mask. And those masks seems detection quite accurate. But we, from our observation, the haze is not a solved problem. So especially we try to check many different geolocation. We find we need to correct the data which was claimed to be already correct already. So this is our challenge. How do we correct the data after send to core transform? And here's our idea. So we also try to train or build a model. We call it haze removal model. So the input is shown on the left, which is a hazy images. And the output, we hope the output can be haze-free. And the first challenge is how do we design a model which can outperform the send-to-core model. The send-to-core model is kind of state-of-the-art in remote sensing area. Next, we also wonder, since how do we teach the model to know the output image is haze-free? Because the input the input image can contain different haze level, and the model need to know how is the input, haze level and output the haze-free. So this is a quite challenging task. So yeah, we go deeper into this problem, and it shows here the first step. We need to index the haze density level. So we show here these two images, they are hazy image, and these two are haze-free image. And from our subjective evaluation, we may think the left image is a higher dense of haze, and this is maybe a light dense of haze. So here we need to index the haze level. And from our survey, we find there's no universal standard for the haze level evaluation, even in industry or academia. So here we try to adapt the dark channel prior. I think the dark channel prior was proposed by a paper. It shows here in 2009. The idea is that from the observation, at least one color channel has very low intensity in some point. And here's an equation to calculate the dark channel prior. So from our experiment, we show here. So this those images are from Sentinel-2 level 2A product. And yeah, we will try to emphasize here, these images should be atmospheric correction, but you can easily see those images are very hazy. And we try to run the dark channel prior, we call, in short, DCP. We run the DCP on each images, and we find the higher value of DCP means higher, density level of the haze. So with this index, we can kind of try to quantize the dense level. So this is a very important step here. And next, here we propose the pi haze data set. So in this data set, there are many image pairs. So for example, this is one image pair. On the bottom is a low DCP, which can means haze-free images. And on the right is a hazy image. So for example, from our experience, we think if the image with this DCP lower than 30, it can classify into a haze-free image. And above, they are hazy. So you can see we can use DCP to quantize the label of haze here. And we also mentioned that, so this is an image pair. Those image pair was captured on the same geolocation, but with different time haze and different timestamp. And those two images was captured within 5 days. So because we try to avoid the ground change between this image pair. And next, this data set cover various terrain type and even the season. So with this proposed data set, and we also come up a pi haze model. And in this model here, this model can input is a 4-channel BGRN remote sensing image. So we design a deep learning model. In the model design, the loss was designed with L1 loss composed of RGBN and NDVI. So we try to train one single model and which can cope with various haze level. So this is an example shown here. So the model input is a hazy image and the output is a haze-free image. And we try to evaluate the RGB loss, NDVI loss, and NIR loss. So this is a model design. And here's a more evaluation result of our pi haze model. So on the left, the x shows the density of the haze. So from light to heavy, and this is a PSNR chart. So you can see that the blue curve is the original hazy and haze-free image. You can see the more haze level, the PSNR will become lower. But the green dot and the orange dot are two of our models with different setting. And you can see our model can perform consistently in spite of different haze level. And the average PSNR is about 30. So this is a more subjective evaluation. Left is an input image about hazy image. And in the middle is a ground truth. And on the right is our model output. You can see our model output, the visual comparison is quite similar to the original one. And yeah, the subjective evaluation shows dramatically improvement. Okay, so here's a quick summary in the second part about haze removal. So from our observation, over 90% remote sensing images are covered with haze. So, haze is a very serious problem, especially in crop growth monitoring, because the NDVI under haze occlusion is incorrect. Next, in this part, we propose the pi haze data set. As we know, this is the largest remote sensing data set we ever collect. So which including over 800,000 image pairs, and each image pair with BGRN 4-channel and with image size 512 by 512. So we also plan to release to public in Q4 this year. So if you are interested in this data set, please contact me in Q4. Next, we trained pi haze model based on the data set. So from our subjective evaluation, the model can work well and also can adapt to various different haze level. Just use one single model. And the average PSNR can achieve about 30 dB. So it's quite well, working well. Okay, so let's go to the third part. It's our pi crop recognition model. The recognition model includes two parts. One is a parcel detection, and second part is a crop recognition. Okay, so this is our task about crop recognition. So when we talk about crop recognition, and this is an example. We try to recognize where is a crop, and actually this is a very challenging task. So it's not a single task. From our view, crop recognition including three tasks. The first is crop length segmentation. So the crop length means, for example, those images are all green area, but if you can see, those are forest, not crop land. So the first step, you need to use algorithm to detect where the forest, where the crop land. And next, we need to do the parcel detection. So this example, we try to segment each ground parcel here. And the challenge is each parcel size is irregular. So the algorithm need to know where the boundary of the parcel. And next, after we recognize the parcel, so the last step is crop type recognition. So for example, this is a rice, this is a maize, and this is a rape. So it's even very challenging to human because all they look green from the visual perception. But we need to train the model how to recognize how is the crop on the ground. So they are not easy. And we have been working on crop recognition years ago. In 2019, we proposed a framework. The framework shows here, this framework can be trained end-to-end, including crop length detection, parcel detection, and crop recognition. So the model input including multi-spectral images, multi-temporal images, so like 4-channel BGRN and the 5 different timestamp images as an input. So this is a deep learning based model, and with this model we can output like the segmentation map, including crop land, non-crop land, and the ridge between the crop land. So next we design topology processing. Well, with this processing, we can connect the disconnect result, like the ridge is broken. So we complete the ridge and make the whole parcel complete. So with this method, we think the framework work well, and this is the result. In 2009, we test this framework on 9 different, we call it proof of concept or testing area. So here's an example. This is a corn crop in Chaoxian here, and this is a greenhouse crop in Shouguang County, and this is a satellite image. In the middle is an annotation with the ground truth, and on the right is a model prediction result. So as we can see, the result is quite, promising. Quite accurate compared to annotation. And here's a table in terms of precision and recall. The average precision is about 90% accuracy. So the result seems very promising. And in 2020, so we try to deploy those testing county and extend to the Grand China. So but we also find one thing: the challenge between POC testing area and massive production are totally different scale, because we encounter different challenges. Here, the first challenge is the data label is very expensive. So in our 2019 model is a deep learning model, so which means we need a lot of training data, and those data need label. The labeling cost is very high. For example, it costs $12 USD per kilometer. Yeah, so when we comes to great area or even cover different crop type, which may cost us $1 million in just human labeling costs. So it's make the mission impossible. And next, when we train the model and we find that the model generation is very difficult because when sometimes, for example, in the China case, the crop seed in the north area and the south area may have different crop seed because some crop seed can stand winter, but some crop seed cannot stand winter. So those different seeds have different appearance from remote sensing spectrum. So this is a quite kind of challenge. Even the same crop, but with different crop seed, different crop breed can cause different spectrum. And we also find when we try to apply the model to the gray area, the different geolocation may have different state of eye condition. For example, some state of eye image was captured in the morning, but some state of eye image was captured in the afternoon. So those spectrum may much look different in terms of the RGB channel. So here's a challenge, it's very difficult. How can we design the model to cope with various geolocation change, crop type change, and even the satellite images have some variation there. And so in 2021, we think out of the box and we redesign everything from our failure experience before. So in this year, so these are core ideas. First, we try to reduce the dependency of the supervised training data or label data. So we try to adapt more machine learning and use less parameters comparing to deep learning model. And we also try to leverage the semi-supervised or unsupervised training to make the model learn from general tasks. And last, we also leverage other sensors like SAR. And because SAR have very, much information, different information compared to the RGB channel. So here's some example. In our model about the puzzle model. The model first part, it will do the pixel clustering. It's shown here. And next, we propose a semi-supervised learning for boundary refinement. So the algorithm will calculate how the close of pixel clustering and try to merge the similar pixel. And this is the output. So we can output a complete puzzle detection. And here's a more result. On the left is input image, and in the middle is the output. So because in this model, we try to learn from general tasks. So we have some presetting threshold for the model. So the model can output different grain size of the detection. So this is an example, this is a fine grain detection result. And on the right is a coarse grain detection result. And from our subjective evaluation, the output is quite promising compared to the ground truth. Okay, next we move to, after we have puzzle detection, next part is crop type detection. So we need to recognize what crop type in each puzzle. So here's our core idea. So we adapt the expert knowledge data set. The model input it, including the expert knowledge. So it's including like the local crop history. For example, some areas cropping history only including rice or corn. So we can limit the recognition type. And we can also know the crop growth period and terrain conditions. We can know which kind of crop can also plant in this area. So next part, we introduce the interactive user interface. This system, I will give more detail in the next page. So with this part, we can make expert or user give some labeling very quickly and easily and interactively. So the model can learn those few label, and we can easily train a model and adapt to different geolocation. So basically, this is our idea. We try to leverage different remote sensing sensors and also leverage the expert data set. And we redesign the recognition system with less parameters. And this is the output. Okay, so this is a more detail about our proposed interactive crop recognition system. So on the left is a map. So the blue dot means a sample point. So each blue sample point is a image raw showing on the right. So for example, this is a one blue point images on different times with different timestamps. And all we need to do is when the user or the expert, for example, we need to give the label. For example, this growth pattern may be like wheat, and if you will, this is a wheat recognition, we just check positive, this is a wheat. And if you check this, if this is the wheat pattern, if yes, just check yes. And apparently this is not wheat, so just don't check. And this is not wheat check. So yeah, so basically we design a user interface, and an expert user can easily just label some positive sample to the model. And every time we press sample, so the model can quickly learn the label and immediately update the result back again. So here's a show average probability, which means the model currently confident about the recognition result. If you think the model is already accurate enough, you just press the deploy. The deploy will deploy the model to the target area and complete the recognition process. So from our experience, we propose a few shot learning, which means we only need a few labels. For in real case, in average we need 40 labels per 10,000 kilometer square. So which quite few labels comparing to the deep learning method. And this is our result. So we try to deploy the model to a massive area. So this is an almond detection in California state in US. The average precision and recall rate here. And this is a corn crop we deploy in Henan province in China. So I think in average, the accuracy is about 80%, but which is quite high enough for the massive area detection. Okay, so the quick summary of our crop recognition system. So crop recognition task is very a core application in agriculture, which is a combination of multiple tasks shows here. And in this part, we first propose the pi parcel module. So in the parcel detection module on the model, we abandon the requirement of huge label data. So we propose a semi-supervised learning for the pixel clustering and boundary refinement. And we also try to train the model from a universal data set, and which can output a multiple label of parcel size. And next, we propose a crop recognition model. In this model, we also abandon the requirement of huge training data. We will introduce an interactive user interface, which can collect the user label easily, interactively, and we try to leverage, synergy the expert knowledge data set, and including SAW, DEM. So the overall performance can about 80% accuracy in terms of precision and recall accuracy. Yeah. Okay, so last I will quickly talk about some interesting analytics in Ping'an. So the first is crop yield forecasting. So the crop yield forecasting is very useful and to some commercial applications. For example, the investment business, they are doing the option trading. So in here, we design a model, the input including remote sensing image, and also include climate data, including the high temperature, low temperature, precipitation. So we design a deep learning model. The model just try to combine the remote sensing value and the weather and output the yield. So from our experiment, we test on US 3 different states, including 250 counties. And the average precision rate is about 90%. So it's quite high in terms of predicting the crop yield forecasting. And next is about flooding and the natural disaster analysis for smart city department. So here's an example. In last year, July 2020, there's a flooding in Hubei province. So in that case, we use multispectral image, star image, and DEM images for flooding detection. And this figure shows before flooding and the area of water coverage. And in the bottom is the water coverage after flooding. So which comparing the two different water detection area. So you can easily see the difference between the water. Sorry, yeah, this is the after flooding and this is the before flooding. So we can see the where is the flooding area. And last is the carbon emission analysis for the ESG department. So, so this example is a carbon dioxide data process for OCO2 satellite. So we download the history data, and this example in 2019, 3 months, and we can do the analysis of the carbon emission. And I think the analysis including interpolation between temporal domain and spatial domain. So this is an example of the in production result. We can calculate each county's emission in the history. Yeah. So with this information, the ESG department can evaluate how the pollution level in each county. Okay, so this is today's my talk is about. So if you are interested and if you have more questions, you are welcome to contact me. Okay, thank you, everyone.